Thank you very much, Vikram. It is really my pleasure to be here, and I would like to thank you for inviting me. It's always a pleasure to share my knowledge and my, let's say, development with other colleagues and friends. And of course, I will be very, very happy to have questions from you because, questions are very helpful for understanding for me. So you are welcome to have a question anytime during the presentation or at the end of it. So yes, since a few years ago, I start to apply the nonlinear dynamics tools, machinery, and knowledge to the field of wind turbines tower, basically because of some grants I got here in Italy, but also because at the European level, green energy nowadays is a very hot topic, the Green New Deal and so on and so forth. So it is very, very important that people put their knowledge in service of this. And our knowledge is nonlinear dynamics, and this is the outcome. So I will talk about internal resonance wind turbine towers and the simple model. So the keywords are basically three. Wind turbines, of course, wind turbines tower, internal resonance, and we will see. And from my point of view and from my, let's say, being, is a simple model. I like to have simple model. I like the phenomena. I believe that to study the phenomena, you do not need the full model, 1 million degrees of free defined elements models, blah, blah, blah. Of course, they will be needed when you will design and check it. But in the preliminary part, when you have to address the problems, you need simple models so that you can, let's say, fully understand the mechanism which is behind, and of course, take care of it, avoid from mistake, from apart, or even exploit it if you believe it is useful. So simple model is the keywords of my talk. So I will start with a brief introduction. I will tell you the mechanical model, which is the simple model I just mentioned. And then I will address the nonlinear problem, and I show you some results of the computation we did. And then I will end with some conclusion and suggestion for further developments that you can be interested to develop. Okay, well, vibration wind turbines are a problem. No way. So let me show, to convince you, let me show you these two, let's say, movies took directly from, directly from, apologize for the advertisement, directly from YouTube, where you can see that, not this one, what happened? Not, this one was the right one, okay? Yeah. This is a very simple wind turbine, so maybe not the most important nowadays, but you will see in a while, let me rush a little bit, how important vibration of the tower, how large they are. Here they are extremely large, and so they become very, very important. Maybe a little bit ahead. When it start to have really huge oscillation, the wind turbine tower, basically because of its slenderness. Where is it? Okay, one more. And you will see that there is, yeah, now we start to have big oscillations. And you will see that when it starts to oscillate, the velocity of the rotation decrease. You see now it decreases. So basically you see that there is many coupling between the dynamics of this structure. And this coupling commonly have a relevance in the, here you can see even better the strong vibration. You see that it stop rotating just because of the vibration. So you really understand how vibration of the wind tower are so important and how they are relevant. So they need to study this for sure. Another example is coming from this video, also from YouTube, and you see this is from inside, and from inside you see how the wind turbine, let's say, oscillate very, very much. So you can imagine that in 100 meters of tallness, this displacement is very, very huge. So I believe that you agree with me that wind turbine vibration is a problem for this kind of structure because it reduces the performance and the lifetime or the life cycle because of the fatigue issues, of course, because with so many vibration, the fatigue becomes a problem. And this is relevant as important for both ground-based onshore and offshore wind turbines, but also for floating offshore wind turbines because of the excitation due to the sea waves. So it's just a matter of the system, not if it is on ground or offshore. And it is triggered by the slender of this kind of structural system because, you know, commonly they are very, very high. Just to give you a number, the tallness could be up to 100 meters with the radius of the cross-section, which is 1 meter. So you see how slender they are. And since they go to very large displacement, they naturally involve the nonlinear regime. So we have no longer small displacement, no longer linear behavior. You have moderate and maybe large top displacement, and this automatically call for nonlinear behavior. So nonlinearity is absolutely needed in this kind of structure. And as you see in the first movie I show you. And nonlinear world is very, very strange because some, let's say, strange, new, unexpected phenomena can occur. There could be the coupled vibration of blades or rotation of the rotor, which is interesting. You saw it before, but is not addressed in this work. In this work, we focus on a very specific problem that, to the best of my knowledge, has not been addressed before. And the problem is this one. Since the wind turbine tower is made by circular cross section, it has the same, let's say, stiffness in two directions. Let's say the direction of wind, that we name along wind, and the direction across wind. Since the stiffness is the same, and of course the mass is the same, you naturally have two natural frequencies that are the same in the direction of the wind and the cross direction of the wind. Actually, they are not exactly the same because the nacelle, which means on top, the rotor, if you wish, there is a little bit offset of the nacelle. So this offset slightly change the one of the two frequencies, but this is very, very slight change. So the two frequencies are very close between each other. So we have in a situation that in nonlinear dynamics, we name it one-to-one internal resonance. And so we want to address this. Why this is a problem? It is a problem because due to the nonlinear behaviors, this entails that excitation in one direction, for example, along the wind or along the earthquakes or along the sea waves, can induce vibration also orthogonal to this direction. Let me name in brief crosswind of the same order of magnitude. And this is only because of the nonlinear coupling between these two, let's say, one-to-one internal modes. This phenomenon does not occur in the linear regime because you are, of course, aware that in the linear regime, the modes are uncoupled. So if you, let's say, force one mode, the other mode, force only one mode, the other mode does not have any excitation and so does not have a response. But when introduced nonlinearity, and because of the strong coupling due to one-to-one internal resonance, when you force one mode, there is some kind of spillover of energy or spillover of displacement that go from the excited mode to the non-excited mode. And this is exactly the phenomenon that we want to study. So this crosswind excitation due to the one-to-one internal resonance. And let me say that this is not a problem if you take into account, but could be a very huge problem if not properly evaluated. Because as always, in engineering, the problem is not, let's say, what happens. The problem is that if something is happening and the engineer does not take them into account, that's really the problem. If the engineers are aware and take care of it, nothing is a problem. The problem is the unconsciousness. So if you are aware of this and you are able to take care of it, it's not really a problem from practical application. Let me say that this phenomena, I mean, excitation along the wind, inducing a vibration perpendicular to the wind, is very similar to the world shedding phenomena, because also in world shedding phenomena, you have the same outcome. You push along the wind and the vibration is perpendicular to the wind. So the outcome is the same, but the mechanism, the motivation is completely different. Not relating here to the world shedding, just one-to-one internal resonance, just nonlinear mode coupling. So you could believe that it is the same phenomenon, but it's actually not. The same outcome, but a completely different phenomenon. Okay, let's move to the mechanical model. Here is basically our tower, the nacelle, the rotor blades. The rotation is known yaw oscillation. We have the crosswind, so a long wind oscillation, which is in the x direction where the wind forces. And this wind could be also earthquakes, could be also sea waves. It doesn't matter where it comes from. Let us name it wind just to fix the ideas. And we can have the crosswind oscillation, the one that can be excited because of this phenomenon I told you. And in this direction, we name this direction as y. And here are a schematic sketch from the top. Here is the wind turbine, x displacement, y displacement, and there is also the yaw oscillation, which is the rotation. And there is also this offset, small offset between the center line of the tower and the center of mass of the nacelle and of the rotor all together, and where we assume that the wind is forcing the excitation. So there is this small offset. This offset is about 1%, even lower of the tall of the tower. So it's very, very slow, but commonly there is. And it will be play a role, as we will see. This is just this one that make the two frequencies not exactly the same, close between each other, but not exactly the same. Okay. So let's go to these simple models. As I told you at the beginning, I love simple models, not very complex model, not finite elements model, very simple models, but taking care of the phenomenon. So here are the 3 degrees of freedom model. You see, 1 degree of freedom is the displacement of the nacelle along the wind. 2nd degrees of freedom, displacement of the nacelle perpendicular to the wind. 3rd degrees of freedom, rotation of the nacelle around the vertical axis or the yaw oscillation. So simply this. And here are the equation of motion after dimensionalization. You see the mass has been set equal to 1. So this follow after dimensionalization. And you have a linear inertia, non-linear inertia due to the between a long wind and rotations. You can have also damping, of course, linear stiffness and non-linear stiffness I mentioned you before, because we are going to have a nonlinear behavior. So this is the nonlinear stiffness due to the bending of the wind tower, just due to the bending of the wind tower. And here is the excitation due to the wind, the F, which is only in the directions of the wind, you see. This is the crosswind displacement. You see here you have no excitation because the wind push all in the other direction. There is no push, no forces in this crosswind direction. And also the rotation, and in the rotation you have basically this excitation, because you see if the wind push along X, it creates, let's say, because of this very small distance, create a moment, and this moment excite force also the rotation, and this is exactly this term which is reported here. And let me say that just to have the model as simple as possible, in the torsional or rotational equation, we have no geometrical nonlinearity. So in this case, the stiffness is only linear, no nonlinearity in this direction. And basically because the torsional stiffness of the beam is much higher than the rotational stiffness. So it is very well founded, this hypothesis, on mechanical base. Basically, this is our very simple, very simple systems. And the parameters are just the nonlinear stiffness, which is the most important, the, let's say, rotational stiffness, and the moment mass of inertia. All of them are, let's say, dimensionalized. And of course, the dampings along the three direction. Yes, as I told you, the nonlinear are only in the displacements and not in the rotation. You see there are no nonlinearity in the alpha equations. And it is a simplified but not poor model sufficient to describe the searched phenomenon. That's the key point. Okay, here are how we pass from the physical parameters to the dimensionless parameter. Just if you want to go back to the real problem, but this is just technicalities. And let me, let's say, underline the main hypothesis I've done. I mean, the second main hypothesis. The first main hypothesis that the model is simplified. The second main hypothesis is that the excitation is assumed to be harmonic. Of course, the wind is not harmonic. So this is basically an approximation, but again, it is a reliable approximation. Why? Because you can take, let's say, the main frequencies of the wind, or from a different point of view, you can select the frequencies close to the frequencies of vibration, because, you know, if the frequencies of the beam, of the wind, is far from the natural frequencies of the system, there are no resonance phenomena, no amplification, and so you are expecting not to have a big vibration, is not a problem. So only when the frequencies of the beam is close to the natural frequencies of the system, because of resonance, in particular non-linear resonance, you have a problem. So assuming, which is an extreme simplification, only one frequency is the excitation, again, is a simplification, is an approximation, but it is reliable to catch the phenomenon, again, to catch the phenomenon, because you are selecting only the frequencies that really make a problem on the system. All the other frequencies that are in the wind do not make a problem for the system because they are out of resonance. So again, this is an approximation, but reliable approximation. Okay. Yes, please, you are welcome.
I wanted to ask if there could be like a drag force along the x direction and a lift force along the y direction as well.
No, because I mean, the force, what you mean, so let's say drag is this one.
Yes, x along x.
And there is indeed, it is just this one, F, you see?
And if there is
the other one, no, because we are not considering world shedding.
Okay.
So we are in a different, let's say, situation. There could be if you have a world shedding, but we are out of this phenomenon.
Okay.
So you can study also that phenomena, of course, will be important, but we are not focusing on that. Okay. Did I reply to your question?
Yeah, yes, thank you.
Okay, thank you so much. So, well, how to compute these nonlinear coefficients? You saw the linear one has been set to 1 just because of the dimensionalization by the elastical. The elastica is a very well model, a simple model for the beams. You solve it. You can do it by, let's say, closed form solution in terms of sinus and cosinus or special function. I don't remember the name, but they are special function. Bessel function. Now another names come to my mind. You can solve it by Bessel functions, and you can compute because of this linear stiffness in the physical problem, the linear stiffness in the physical problem, and the K3 is just this ratio. And you can see that this K3 is just a fixed number, and the ratio between this offset, remember that D is the offset, here is the offset, and H is the toll of the tallness, yes, the toll of the tower. And you see that it is D over H, which means that it is a small number, which means that small square, it is a very small number. So this K3 common, it is a very small number, it is reported here. On the other hand, here it is, the linear torsional stiffness, this K alpha, is the ratio between the flexural stiffness and the torsional stiffness. After the dimensionalization is basically H over D, so the opposite. So this means that it is a very large number, very large square, even large. So K3 is small and K alpha is a very large number. This means that this stiffness is almost not exact because of very large stiffness. That's why we can, let's say, forget about this nonlinear cut. Anyway, we do this. So let's go to compute the natural frequencies of this system. So we linearize our problem and we forget about the damping and the excitation. And here are the equations, the linear equation. And you see that the linear equations are a long wind and crosswind and torsional decoupled. You see only X here and only Y and alpha in the last two. So we have a long wind X decoupled from the others because of the linearity. Because in the linear regime, you know that the modes are decoupled. So we are not surprised. And if you compute the natural frequencies of this system, you have the first one, which is 1, coming from the one, and it is the natural frequencies along the wind. Of course, it is just 1 because of our dimensionalization. Of course, it will be a number in physical dimension, but this number will be set equal to 1 after the dimensionalization. And the two other frequencies related to the Y, which means crosswind, and alpha, which means rotation, let's say modes, are given by these equations that written in this way is not so clear, but let's say, remember that K alpha is a large number. You remember K alpha is a large number. So if we develop this term as assuming that kappa alpha is large, you see that omega 1 remain 1, omega 2 become 1 minus some things, omega 3 becomes square root of K alpha over square root of EP plus some things. So you see that here it is the internal resonance, 1 to 1. Not exact because there is this little bit difference, but this difference is very, very small because K alpha is very, very large. So we have what I said before, just an internal resonance, and the tuning parameter, which means the difference between the two close frequencies, which is omega 1 minus omega 2, is just 1 over 2 K alpha, which is a very small number, as I saw before. Here you see that K tray is very large because it's proportional to K alpha. Very large means that it is not relevant for our phenomenon. So we will focus only in this internal resonance between omega 1 and omega 2. Omega 3, the third natural frequency, is not relevant for us and will not take care into account. So here we have the proof, as expected, we are not surprised that we have an internal resonance. And please consider that the is not exact internal resonance just because of this offset kappa, because offset D. Because if D, which is, I repeat, this offset, if this goes to 0, apologize, there is some noise from my university. If this goes to 0, K alpha goes to infinity, and if K alpha goes to infinity, this goes to 1, and you have perfect internal resonance. Okay. So, sorry for this interphone coming from communication in my university. I'll wait for ending.
Maybe, Stefano,
yeah,
this opportunity during the break question that I just typed there. So in a typical citation, we have a constant wind speed, which is not a problem. But then there's plus the sampling of the wind turbine blades of the wind, which is a function of how fast the wind turbine blade is rotating, and then the frequency spectrum inverse, which is the turbulent part. So in your analysis, you're taking the turbulent part close to the natural frequency, which is sine omega t. But natural frequency, because you have nonlinear, is not a constant. So it's amplitude dependent. It's dependent to a certain extent also on the function of the rotational frequency because of centrifugal forces. So what I'm asking is, should we, apart from just having sine omega t, do we need to add another sine capital omega to represent the rotation of the turbine blades and the small omega as a function of both amplitude representing the nonlinearities, and then do the analysis and then omega to these terms will probably change and the zone of resonance and instabilities will change? Or do you think your larger terms will still dominate?
I mean, what you say is completely right. Is completely right. I mean, there will be, let's say, this kind of coupling between and the so amplitude dependent and natural frequency because of nonlinear regime. But as I told you, we are at the beginning of this research. So at this stage, for us, the excitation is just sinus, here it is, sinus omega t. Then this omega can change because of the rotation. I fully agree with this. I fully agree with this. At this stage, we have not added this dependence. We do not take care directly of the rotation of the blades in this model. The rotation of the blades is just hidden behind this omega, but for sure this omega will depend on the rotation of the blade. And for sure, this is one of the developments we have to perform, for sure. So I fully agree, but let me say that I am in the preliminary stage. So since, let's say, internal resonance not yet been discovered before, to the best of my knowledge, maybe I'm wrong, but to the best of my knowledge, so I want to do it in the simple way as possible. But for sure, what you say should request to be investigated. And if you are interested to do, please contact me. I will be very happy to do it together. I will for sure very happy, and for sure this is worth further investigation, for sure. I reply to your question?
Absolutely.
Thank you. Thank you. Okay, so now we have checked this internal resonance, and let's say solve this internal resonance problem. We apply the multiple time scale method, looking for a solution in this form, introducing the small bookkeeping parameter epsilon. And again, the external excitation is harmonic, which is rough, but enough for the purpose of lighting the phenomena in a simple way. That's the key point. I glide the phenomenon in the simple way. That the rotation of the blades, the oscillation of the sea wave, if you are a floating offshore with for sure will play a role, for sure. But this will come later. Now we want to highlight the phenomenon. Okay, so we look for the solution in this way, where T2 is the slow time, T0 is the real time. There are some technicalities, of course, that I will skip. We will exploit both the internal resonance as we saw before, so epsilon is related to this detuning, and also external resonance, because as I told you, we have a problem only if the external frequency is close to the natural frequencies. Otherwise, if the external frequency is far from the internal frequencies, there are no resonance, and so it is not a problem. And I fully agree with the comment before. These natural frequencies that here we consider the linear natural frequency, which is, let's say, amplitude dependent. In a more improved model, this natural frequency omega-1 could be amplitude dependent because of nonlinear behavior. So I fully agree that these natural frequencies could be, let's say, amplitude dependent in a more sophisticated way, not in my model. So later on, next step, and you can have, let's say, external resonance for a different frequency. Fully agree, but not in this model. And this sigma internal is just the internal detuning that basically this sigma I is given by this, here it is, 1 over 2 K alpha. Okay. Well, a lot of computation. For sure, I will skip the computation. I don't want to bore you with the computation. You have the first order problem, the linear one, the first order solution, which is reported here, the second order problem, and you introduce the second order solution, which is reported here, the second order solution. You have the third order problem, and the third order problem, you have some, let's say, secular terms. You have to avoid the secular behavior, so you have to introduce some solvability problem. I will go very, very fast because my talk is not on the technicalities of the multi-time scale method. If someone is interested, can contact me, or there are some books, mainly by Nefi, that are very, very helpful. At the end of the day, you end up with these two equations in the two unknowns AX and AY. where AX is the amplitude. Let me go back. What is AX? Here it is. AX is the amplitude of the along wing oscillation. AY is the amplitude of the crosswind oscillation and also of the rotations. So AX along wind, AY crosswind. Two amplitude, these are complex amplitude, and you have these two equations, the first one and the second one, to compute these two numbers as a function of the detuning, as a function of the external frequencies, which is here, sigma E, which is the external detuning, which contains the external frequency, as a function of the damping, and as a function of the structure. So basically, we are just to solve these equations. Following the standard, let's say, machinery of the multiple time scale method, you introduce the real amplitude, because these are complex. So you introduce small, lower capital AX, which is the real amplitude of the oscillation along the wind, AY crosswind, and you transform, let's say, you write the first order and the second order solution in terms of this AX and AY, and you see that AX is really the amplitude of the X1 oscillation and the amplitude of Y1 oscillation, so first order amplitude, and they appear also in the second order solution, of course, with square behavior, because it is second order. So just to give a meaning to what AX is and AY is. So they are the physical amplitude of oscillation, even though they are in dimensionless form. Okay, and you transform this solvability condition in the real and imaginary part. So basically you have four equations that are the modulation equation reported here. Again, mathematics, I will skip it. I don't want to bore you with mathematics. You are looking for physical periodic oscillation, which are equilibrium of the modulation equation. Basically, you set these derivatives with respect to T2 equal to 0. So equal to 0 the first one, equal to 0 the second, the third, and the fourth, basically. And so you end up in four algebraic, that's really a big point, algebraic, nonlinear, of course, because we are in nonlinear regime, four algebraic nonlinear equations in the four unknowns, amplitudes and phases of this solution. The phases are, you see also there is a phases, which is the time difference between the excitation and the response along wind, phi x, and across wind, phi y. So basically, four algebraic nonlinear equations in four unknown. And this can be, let's say, easily solved. On top of that, you can eliminate the phase if you have only two equations in the two unknown AX and AY. 0 stands for equilibrium, which means oscillation in the physical meaning. And you have just to solve these two equations. The two equations are fourth order the first one, eighth order the second one, but only, let's say, even power. So basically means this is the second order and this is fourth order. So maximum you have 80 coexisting solutions. And now we have just to analyze, to solve this system and to analyze the solution from a mathematical point of view. And you see, this is a function of the wind excitation and also of the excitation frequencies. Okay, let us start to analyze this solution. So first, let us recognize that there should be the along wind solution only, because of course, if you push along the wind, we expect that we have a long wind solution only. So solution that have displacement along wind, AX different from 0 and AY equal to 0. No displacement along wind. Well, you have this solution. You can, if you give a look to this equation, you can find this solution. And this is the classical solution of the Duffing equation. And here you have the so-called backbone, the frequency response curve, where you have the external frequencies as a function of the excitation. So here everything is standard and everything is as expected. But what we are looking for is something different. This is expected, you find it, but we are looking for different solutions, other solutions. We are looking for coupled solutions with a long wind and crosswind, which means we are looking solution having AX different from 0 and AY different from 0. That's exactly what we are looking for. That's exactly the new phenomena that we are looking for. This uncoupled solution is already known, nothing new in this slide, nothing new. So, before found this, let us discuss also the stability. The stability is addressed by computing the gradient of the modulation equation, computing the eigenvalues. If all the eigenvalues have real part lesser than 0, the physical periodic solution is stable. If at least one eigenvalue has a real part larger than 0, the physical periodic solution is unstable. This is again quite standard. This is at let's say undergraduate level, so nothing new for you, but just to remind that we will use the real part of the eigenvalues to determine stability. And of course, the bifurcation, which means the change of stability, the passage from stable to unstable, which is exactly what we want to avoid in practical application, occur when the maximum real part of these eigenvalues become equal to 0. And if this happens when the imaginary part is equal to 0, we have the pseudo-null bifurcation. If this happens when the imaginary part is different from 0, we have a Neymar-Sacker bifurcation, or the secondary off, if you wish, which means that the quasi-periodic solutions are born. This is quite technical. I have no time to go into the details, but you have to trust me for these slides. And all these three bifurcations, because also a pitch for bifurcation can happen because of let's say, symmetry. All these three bifurcations are seen to occur in the next example. Okay. Let's go to the example, stop computation, just see some results. Here we consider NRL 5 megawatt reference wind turbine, which is the most famous one in this field. It's not the real one, but it is a reference one which has been, let's say, agreed by all the wind engineer community as a reference. So everybody that works on wind turbine use this wind turbine as a reference. Here are the physical parameters that you can find on the NRL website. So these are open access data. With this data, you have these dimensionless parameters. And you remember that K3 should be a small number. And you see how small is this number, 0.0004. And maybe you remember that K alpha should be a very large number. And you see how large this number is. Of course, small and large mean always with respect to 1. And here is the damping that we assume. We assume 5% of damping, which is a quite high value with respect to for real problem, but just to start with. Of course, in the next simulation, we will reduce these numbers because in the real world, this damping is a little bit smaller. And from this basic parameter, we have the derived parameter, the omega 2, omega 3, the tuning, and blah, blah, blah. You see the omega 2, how close is to 1. And so you confirm that we have an internal resonance. And you see the omega 3, how large it is, confirm that this omega 3 is not a problem for us. Well, here is the first result. Here is a crosswind, so along this direction. Along Y is, this is along wind, along X. A crosswind, and this is the frequency. Basically, sigma Y is the difference between natural frequency and the external frequency. Well, you see that this curve is the classical resonance curve that happens when AY is equal to 0. This is the classical uncoupled behavior. What is expected? This is just these slides. So the uncoupled behavior, exactly what expected. Classical, slightly bend toward the right because we have an hardening behavior, nonlinear response curve. So nothing new. The new part is just this black curve. You see, at a certain level, from this uncoupled behavior, a coupled behavior starts, and you can have crosswind oscillation. AY start to become different from 0. So oscillation in the direction perpendicular to the wind, start and do this kind of curve. All this curve is stable and the phenomenon is there. And here is the amplitude and the frequency where this phenomenon triggers. So we have shown that in this model you can have this phenomenon. So basically this is our, let's say, main result, our main finding. This phenomena, this coupled oscillation happen, and you are also able to compute when it happens. It happens at this threshold. Please note that it is not, let's say, unexpected, that does not occur from the beginning, because for very low frequency, for very low amplitude, is the linear regime that dominates. And in the linear regime, the two modes are decoupled. And so in the linear regime, if the two modes are decoupled, forcing in one mode does not produce displacement in the other. Only if you go to the, let's say, nonlinear regime, which require quite large displacement, you can have coupling, and indeed, all in moderately large displace, you have this coupling. Well, that's basically our main result. This is phase projection of the same picture, so nothing new in this picture. If you increase this happen for f equal to 4, which is the amplitude of the excitation, if you increase the excitation amplitude, not only you see that the bending is increased, but the phenomena is still occur, of course, and this, let's say, coupled wind can become unstable. Initially stable, black is stable, red is unstable, and on top of that, this can involve pitch bifurcation, where this phenomenon occurs, saddle node bifurcation, Neumann-Sackel bifurcation again, and let me say that in this red curve, you have quasi-periodic oscillation. No more periodic oscillation, but just quasi-periodic oscillation. So very, very complex behavior. And again, we are happy with this, of course. Let us increase again the excitation frequency up to 10, even more complex behavior, up to 20, more and more complex, more bending in the coupled mode. But again, there is a branching from the gray, and the gray is the uncoupled mode. That is what you are expecting if you are not taking into account this internal resonance. Okay, again, the projection. They are all together just to show what happened by increasing the excitation amplitude. F is the excitation amplitude. Start here, more important, even more important, and even more important. Okay. Now, let us collect here the values of the excitation amplitude when this phenomenon triggers as a function of F. And you see this picture, and you see that it activated for increasing amplitude, increasing excitation amplitude is activated for these values of the, for these critical values of the vibration along the wind, and also for these critical frequencies. And what is interesting is that you can compare here the black curve, which is obtained by our, let's say, multiple time scale method approximate solution, with the blue curve, and the blue curves come from numerical simulation. So from exact, let us say, exact result, and you can see the perfect matching, which means that the multiple time scale method provide you a very reliable approximation. Here are some examples of vibration for a fixed value of the frequency. For example, for if equal to 7, and for these external frequencies, you see, let us put in this, this picture, for example, along wind X, cross wind Y, and you see how the solution is. You see, basically it is an ellipse, and again, black is numerical, black is analytical, and blue is numerical, and you see the very good matching, and you see again that you have not only oscillation along the wind, along X, but also oscillation across the wind. So as I told you, the match between the, let's say, analytical black and numerical blue solution is not as good if you consider the, let's say, rotation amplitude, But please note that rotation amplitude is very, very small with respect to the others. And remember that we are in the dimensionless form. So forget about the fact that it's 40. 40 is dimensionless. Here it's 0.02, so this is basically very small. And of course, one of the next step is to improve our solution to try to reduce this difference, this gap between analytical and numerical solution. Basically, we see that in rotation, we have the effect of some other harmonics that have to be taken into account that have not been done up to here. Okay, again, just to check our result, a comparison between, let's say, analytical, let's say, bifurcation diagram coming from the previous one and numerical bifurcation diagram. And you see in numerical bifurcation brute force, you capture only a stable solution, no unstable solution. And you see that you catch this one, then you go there. So this one gray, then you go there. And here, when you have quasi-periodic, you found in numerical simulation quasi-periodic solution. And again, you jump back to non-resonant branch here, which is reported here. So perfect agreement between numerical simulation, we are happy. Again, perfect agreement also in terms of maximal crosswind displacement, Y, and also maximum rotation, and blah, blah, blah. Here are time history of the quasi-periodic solution and phase portrait of the quasi-periodic solution. The quasi-periodicity is confirmed by this Poincaré section, because the gray are the full time history, the black are the time history sampled of each period, which basically is a Poincaré section. And you see that in the Poincaré section, you have a closed curve, which confirm that you are dealing with quasi-periodic solution. Again, quasi-periodic solution, but it is basically the same result. Yes, I go to finish because I don't want to bore you that much. Of course, to confirm that this phenomenon is not episodic, we change the parameter. So we move to different values of parameter, just to be sure that it is, let's say, a robust phenomenon, not happening just in that simple case on NRL 5 megawatt. And we chose this parameter, and again, the phenomenon is there. So the phenomenon is robust. The phenomenon is there. Here are just other projection and blah, blah, blah. Basically, that's what I want to tell you. And let me conclude, say that a long wind, a crosswind coupled oscillation of wind turbine tower has been investigated in correspondence of one-to-one internal resonance. We have used a 3 degrees of freedom simplified model, for sure to be improved. We already discussed about this. But this model is able to exploit the phenomena. And the multiple timescale method is used to be obtained an analytical approximate solution. We, let's say, use a NRL 5 megawatt reference wind turbine as an example to show you some result, and the frequency response that could have been illustrated. So, yes, the branching has been shown, the parametric analysis has been reported, complex behavior illustrated, the presence of saddle node, pitchfork, and Neymar cycle bifurcation and glide. But I would go to, let's say, further developments, and the further developments is relaxing various hypotheses that has been done. One has been already mentioned, and for sure it is one of that require further development. And check whether couple long wind and crosswind oscillation still exists by relaxing these hypotheses. This commonly will require EV numerical simulation, could require EV numerical simulation, but we can do it if you want to get closer to the real problem. And of course, the next step is to compare with experimental results. In this direction, we are working with the people from the Netherlands that provide us, let's say, some experimental result. And in these experimental results coming from real wind turbines, he was able to show experimentally this a long wind, a crosswind, let's say, coupled behavior that for us could be related to this internal resonance. We are making a more detailed comparison. I have a PhD student that is working on this, and I hope that in a couple of months we can, let's say, confirm our finding with experimental result. But to date, I don't want to say nothing because we are the check is still is still ongoing. So I want to be sure before saying that our result has been confirmed by experimental result. We are not yet in this stage, but I hope to be in this stage soon. And basically that's it. Let me close with a couple of announcements. Next year in June, here in my city, I will organize a UTAN symposium on nonlinear dynamics of system structure for green energy generation, which is strongly related to this, the topic of this talk. And so you are kindly invited to contribute. If you are interested, please send me an email. You are very welcome to receive your contribution in the application of green energy to the linear dynamics to green energy generation. And please remind that this green energy in general, not only wind energy. So any other of green energy is welcome. And the second announcement, we are looking for developing the participation of the nonlinear dynamics commuting within the European mechanics journals, where I am an associate editor. And so please, if you have good paper, please send it to this journal. We are very welcome to receive your very good papers. So thank you very much.